Welcome back, everyone. Thank you. Thanks to our first two speakers, and our last speaker to the contributed talks is given by Frederick Pardoe. Frederick is a PhD student at the University of Illinois at Urbana-Champaign, and he will talk about spin-up and mass gain in hyperbolic encounters of spinning black holes. Frederick, please continue.
Okay, so as was just said, I'm Frederick, or I go by Freddie. I'm a graduate student at UAUC, and I'll be talking about the spin-up and mass gain in hyperbolic encounters of spinning black holes, which is a project that I conducted in collaboration with Healy Kogan, who was formerly an undergrad in our group and is now studying at Stanford, and my advisor, Healthy VTech, who gave a nice talk yesterday, if you saw that. And we recently sort of submitted this to a journal, and you can find the archive link here if you'd like to take a look at that. So to start, let me just say a little bit about like why these systems are interesting to study. So typically, hyperbolic encounters, which is sort of the interaction of at least initially unbound black holes, are probably most likely to occur in globular clusters, which are these very dense systems of black holes and stars. And so in these systems, we'd expect to see lots of sort of mergers and sort of these hyperbolic encounters. And furthermore, it's sort of interesting to consider how the spin distribution of the black holes affects these sorts of interactions, because we know, for example, that black hole mergers often create spins as high as 0.7, and sort of various studies modeling how the spin kind of distributes in globular clusters show that after several interactions, they could be anywhere from between like 0.4 and 0.9, depending on the different sort of assumptions and in the models and the properties of the clusters they use. So I think we've heard a bit about hyperbolic encounters already today, but just to kind of say a little bit more, if, for example, we consider this setup that I have shown of the equatorial plane of a binary black hole encounter here, and we sort of consider that our black holes, in this case, are equal mass and have some sort of incident scattering angle and equal but opposite initial momenta pi, then if you sort of choose a large enough initial momentum, then at least initially these black holes will be sort of unbound in a sort of classical sense. But if you decline if the incident angle is small enough, then when the black holes get near each other, they will lose a bunch of energy due to gravitational wave radiation, which will cause them to sort of become bound dynamically and then merge. At sort of intermediate angles, there's this property unique to GR where the black holes undergo this succession of relatively large eccentric orbits, punctuated by smaller, very circular orbits before they eventually merge, called zoom whirls. And then at very large angles, you get what you'd kind of expect classically for a hyperbolic encounter, which is these scattering orbits where the black holes just get near each other, pass by, and then go to infinity. And it's really these scattering configurations that I'll be focusing most on today. So now let's talk a little bit about what the spin-up and mass gain are. So if we, for example, consider a system where the black hole spin is zero, just a starting point, and here I have kind of like a side view of the diagram that I showed before. Then as the black holes scatter and they sort of get close to each other, they'll emit a bunch of gravitational radiation, and they will also sort of reabsorb part of that radiation. And due to the reabsorption of that radiation, they'll gain a little bit of angular momentum and mass. And so that's ultimately causes this increase in the dimensionless spin and black hole mass. And so these phenomena have been kind of studied in a variety of different initial conditions. And then I'll talk a bit more about the exact conditions that we'll focus on here in the next slide. Okay, so here we considered systems entirely with rotational symmetry. Again, we're looking at a sort of top view here. Then if we look at a side view, we're very interested here in looking at how the initial spin affects these dynamics, as well as the incident angle. And so to maintain the rotational symmetry, we restricted our study to initial spins aligned with the z-axis, which is also the same axis as the orbital angular momentum of the black holes. And in what follows, if I use a positive spin, that will refer to a spin that's aligned with the z-axis. And if I use a negative spin, that will be a spin that's sort of anti-aligned to the z-axis. And so there's a variety of different quantities that I'm going to look at in sort of understanding this phenomena. One is just the sort of change in spin, which I'll typically refer to as the spin up or possibly the spin down if this quantity is negative. And I'll also look at the dimension full spin or sort of angular momentum of the individual black holes. Furthermore, I'll look at the mass gain, which I'll report as a relative change since the mass is sort of positive definite. And then we also sort of know that the mass can be decomposed into an irreducible component that's related to the horizon area and a component based on the black hole angular momentum. And so I'll also be looking at how the change in this irreducible component compares to the change in the sort of total Christodoulou mass. Okay, so to start, let's look at the spin up of the black holes. So here I'm plotting the spin up against the instant angle when we use an initial momentum of 0.49 in terms of the total black hole mass. And these different lines here correspond to different initial spins in the simulation. And so you can see, for example, that in almost all of these cases, the spin up increases for smaller instant angles and also for smaller or more negative initial spins. And sort of the maximum value that we see in our simulation suite, at least for scattering simulations, which this is restricted to scattering simulations, is about 0.3. One thing that we sort of made a point of doing is looking at how this effect how this behaved if we sort of focused on the lowest angle for which we found scattering simulations, so sort of the threshold between scattering and merger. And if we plot the spin up against the initial spin under these conditions, we see that there's a sort of remarkably linear trend between the initial spin and the spin up. And here I've plotted that for two different momenta which we considered. I only plotted one here for the sake of time and space, but you can kind of see how those are a little bit different as well. But if you look closely, you should also notice that the simulations with initial spin of 0.7 behave qualitatively a little bit differently than the simulations with lower spins. If you look closely, there's kind of a curve here. And so this is what I'll focus on a bit more in the next slide. So here, in order to sort of understand how the initial spin 0.7 simulations behaved, we ran these simulations for a variety of different initial momenta from between 0.245 to 0.6125 in terms of the black hole mass. And as you can kind of see here, I plot again the spin up against the threshold angle. The sort of qualitative behavior of the spin up as a function of the threshold angle changes a bit as a function of the initial momenta. But what I really want you to sort of notice here is that in this case, the spin up is actually negative, which shows that the spin is sort of increasing contrary to the direction of the initial orbital angular momentum. And so effectively, we have a spin down. And we can kind of gain some insight into why this is happening if we look at the corresponding change in the black hole angular momentum here. This is the angular momentum of the individual black holes, not the orbital angular momentum. And what's interesting here is we can see that although the spin is sort of decreasing, the angular momentum is also pretty much always increasing, at least within numerical error. And essentially what this tells us is that the reason we observe a spin down at this high initial spin is because the increase in the mass of the black holes is sort of outweighing the increase in the orbital angular momentum. So if you recall how the dimensionless and dimensional full spin are related, that means that there's kind of decline in the dimensionless spin. So on that note, let me talk a little bit about the mass gain of the system. So here on the top, I'm plotting the mass gain of the total Christodoulou mass, sort of in like units of percent, the way this is scaled, as a function of the instant angle. And like before, we can see that much like with the spin up, the mass gain tends to increase for lower instant angles. and sort of lower or more negative initial spins, at least if you kind of look at examples where the instant angle is the same. And the irreducible mass behaves largely qualitatively similarly to that, that it obeys those two trends. But we can sort of observe some other interesting phenomena if we again look at how this behaves if we fix this to the lowest angle for which we have a scattering simulation. So if we plot this at the sort of scattering merger threshold.
Frederick, you have 2 minutes.
2 minutes. Okay, I'm almost done. So if we look at sort of the mass gain here against the initial spin, we can see that the mass gain for the total mass in black is relatively uniform as a function of the initial spin. But for negative initial spin, the relative change in the irreducible mass is actually greater than the relative change in the sort of total Christodoulou mass. And physically, the reason for this is that when the initial spin is negative, when the black holes sort of spin up, that means the magnitude of the spin has actually declined. And so that means that that decline in the spin magnitude kind of contradicts or counteracts the increase in the irreducible mass, if you remember that formula from earlier. Okay, and so I think I'm low on time, if that's correct. So maybe I can just stop here and take questions.
Oh, you can continue with this.
Or, oh, okay. There's 2 minutes for questions. Is that part of the 2 or?
Yes, yes.
Or, okay. Anyway, so I guess just to summarize, we find that there's a spin up that is kind of decreases with instant angle and, increases with decreasing instant angle and initial spin or sort of negative initial spin. We find spin ups as large as 0.3. Sort of interestingly, we find that when we look at this at the scattering merger threshold, the trend is very linear. And we also find that as you increase the initial dimensionless spin, at some point you start to see that there is a decrease in the initial spin where the change is sort of contrary to the initial orbital angular momentum. We also find that there's a fairly substantial gain in the black hole mass. The largest changes that we find are about 8%. And what's sort of notable, although when you sort of think about the Christodoulou formula is perhaps not entirely unsurprising, is that for anti-aligned negative initial spins, the change in the irreducible mass is greater than the change in the total mass. And there's other things which I sort of cut out for the sake of time, but if you'd like to see what else we looked at, you can look at the draft and archive here.
Thank you very much, Frederick. Very, very nice talk. Let me stop recording.